Hello guys, welcome to my video. Okay, so today I'm going to be solving the May-June 2023 question paper 134 physics, and the question paper is 1 hour 15 minutes long. So I'm going to be going through some of the questions and how you are supposed to answer them. So please, I hope you have tried out the paper so that you can be able to see how some of these questions might be answered. And I'm going to be going through some of them, explaining in detail how you're supposed to answer most of these questions. So if you like the content, please like, comment, share, and please subscribe to my channel so that it can be able to reach more people. Okay, so let's begin. The first question: what must be included in a record of a physical quantity? So the first thing that we need to understand is what exactly is a physical quantity. Okay, so a physical quantity basically consists of two things. Number one, it consists of a numerical magnitude. Okay, consists of a numerical magnitude. And number two, it must consist of a unit. Okay, but you need to understand we have three kinds of units. Basically, there are many kinds of units, but the units that we have can be SI base units, SI base unit. The second one is a derived unit. Okay, and the last one is a base unit. Okay, so you need to understand that there are three different kinds of units, and the SI base units basically refers to the international system of units, the Le Systeme International de Unités, well, which are basically the base quantities that we know, which are 7, as you can see on your screen. So those are the SI base units, and the derived units are basically units of derived quantities. It can be power. There are a lot of quantities that are derived, okay? And the base units are basically the units of those base quantities. But a physical quantity can have any one of those three, which makes B wrong because B assumes that it's only an SI unit that makes up a physical quantity. And it makes A wrong because A wrong is saying it has to be an integer value. But a physical quantity can also have a non-zero value, which can also be negative, okay? But this answer is only limiting us to only positive or negative whole numbers only, because an integer is a positive or negative whole number, okay? And the last D says a unit expressed in base units. Again, that unit can also be expressed in derived units. So the correct answer is C, which is a numerical value for the quantity. Okay, very important. Move on to the next quantity. We've been asked what is the ohm expressed in SI base units. So you need to understand exactly what is the ohm. So the ohm stems from resistance. Okay, so we know that resistance is equivalent to voltage divided by the current. From the table, V is equal to IR. Resistance is actually the voltage divided by the current. Okay, but we know that the voltage is actually the work done per unit charge. Okay, so the work done per unit charge is basically the resistance itself. Okay, the work done per unit charge is basically the voltage itself. So the work done per unit charge is basically the voltage itself. Okay, but work done basically, or energy transferred, think of it this way. The units will basically be the same, okay? We know that work done is equivalent to force times distance, and the units of force are kg m s to the power of -2 multiplied by m. That gives us an overall force of kg m squared s to the power of -2. So the units of volt would therefore be kg, okay, m squared s to the power of -2 divided by, but q is actually as, right? Because it's current times time. So the units would therefore be AS. That gives us the unit of voltage to be kg m squared s to the power of -3 divided by AS, which would just be kg m squared s to the power of -3. Okay, sorry. So this is -2. That would become s to the power of -3 and a to the power of -1. So those are the units of voltage. But if you have those units for voltage, the units basically of resistance would just be those units, kg m squared s to the power of -3, a to the power of -1, just divided by a. Okay, so that gives us kg m squared s to the power of -3, a to the power of -2. Okay, so the correct units are therefore, the correct answer is A. Okay, move on to number 3. Okay, question 3. We've been given a desk that has a true width of 50. So basically this is our true value. Okay, so let's just put it there. That is our true value, okay? Two students, X and Y, want to measure that width of the desk. So think of this desk that I've given you on the side, and its true width is actually 50 centimeters. And two students want to measure that desk. Now, student X takes a measure and records a width of 49.5, okay? So that's quite accurate because the true value is 50, meaning this actually lies in 49.0, actually all the way to 50.0. So it's pretty accurate. The next student measures and gets a width of 51.4 plus or minus 0.1. So basically lies around 51.3 to about 51.5. So we can obviously see that student Y is not even accurate because it's not close to the true value itself, right? But it's quite precise because look at that range of error, right? He has 0.1, so the values are quite precise, right? Because it is a very small range. So a small range talks of how precision is present, okay? So a very small range means that you've gotten the value very precisely, but a very wide range means that you're not so sure, so your range is quite big, means that the precision is quite low, okay? So student X actually has a more accurate, okay, but so B and A are wrong. It is a more accurate, but the problem is they're less precise, okay? So it's more accurate, less precise. The answer is D. I'm moving to question number 4. We've been given two vectors X and Y that are drawn to scale, okay? But X is equivalent to Y minus Z, and which diagram represents the vector Z. So what can we do here? Well, we can actually rearrange Z. We want to find the value of Z, right? So I know that Z is actually equivalent to, from that expression, Z is just equivalent to Y minus X, okay? So it's just putting the Z to this other side, taking that X and putting to the other side, okay? So that gives us this expression, meaning Z is actually Y plus negative of X, okay? But the negative of a vector means you take that same vector, but you just reverse its direction, okay? So it's basically that same vector, but that vector just with an opposite direction, okay? So that same vector, but that vector just with an opposite direction, okay? So something like that. This would actually be the vector of negative X, right? So this is the vector that we're taking, and we're actually going to join it to that, and we're going to form the vector Z, okay? So I want to teach you something about the triangle method, okay? So whenever we talk of forces, when forces are arranged in a closed triangle, the resultant force, which is the value of Z actually that we're looking for, is just you closing up the triangle and creating a continuous triangle, okay? So this is what I mean by this, okay? So if you have a force basically that is acting in that direction, okay, and you have another force that is going down, okay? So if you have another force that is going down like that, okay, so if you have two forces like that, the resultant of these two forces will actually be a force somewhere in that direction, right? Which will be acting in that. So this is just us considering if So this is us just considering if two forces act at one point, right, and they branch in two directions, the resultant force will be from that center going down in a particular direction, right? Okay, so very important. So you can actually find the resultant force because this is quite different, right? So you can usually find the resultant of two forces if you're going to join them at one particular point, allow them to go in two separate directions, and your resultant force will be stemming from that particular point itself, okay? So if you're going to draw it again, it's basically saying if you have that force here and you're going to go over there and they're going to act at a common point, right? If they're going to act at a common point like this, the resultant force has to stem from that common point going in that direction. Because if you have a force that's pulling down, right, if you have a force that's pulling at that angle, like sort of slightly down, you must also have a resultant force that is basically down, right? It can't be a resultant force acting up in the like that. It can't be a resultant force that is actually going to be like pointed up like that or that. So the answer has to be A. Okay, so very important, right? I'll move on to the next question. Which equation representing uniformly accelerated motion in a straight line can be determined using the definition of acceleration? So what is acceleration? Acceleration is basically the rate of change, okay? The rate of change of velocity, right? How fast is velocity changing? So acceleration is basically the final velocity minus the initial velocity divided by time. But I know that AT would therefore be V minus U. Therefore, V will basically be equivalent to U plus AT. So I can just get this expression only just by me stating the definition of acceleration. I can't get A, I can't get B, and I can't get D because that is not the definition of acceleration. Very important. I'll move on to the next question. An object moves from rest, okay, with uniform velocity that is horizontally and uniform acceleration that is vertically, okay? So which graph shows the variation with time of the displacement of the object from its initial position that is shown correctly. Okay, so what can I do with this? Well, one scenario that I can think of is imagine you have a ground over here, right? So it's more like a projectile, but we're firing it from rest with a uniform velocity. Okay, so let me create something like this. Okay, basically we're going to create a cliff or something like that. Okay, and we're going to fire our ball, which is somewhere over here, right, with an initial horizontal velocity. So our ball is going to go down over here, and it has an initial horizontal velocity in that direction. Okay, so that's the initial horizontal velocity, right? And uniform acceleration vertically downwards, so the acceleration going down is actually equivalent to the value of g actually going down. Okay, so we've been asked to show the variation with time of the displacement of the ball from its initial position that is shown. Okay, so I remember guys, whenever you see graphs, you need to think of three things, right? I always say this. You need to think of your axis, number one. Number two, you need to think of area under the graph. And number three, you need to think of the gradient of your graph. So get this. The gradient of a displacement time graph represents velocity. But if you're going to tell me that velocity is uniform in the horizontal direction, then I should expect to see a uniform gradient. Meaning that in the horizontal, I need to see a gradient like that, okay, or a gradient like that, right? So basically that's a uniform gradient, showing me that acceleration is basically uniform in that direction itself, okay? So something like that, right? But it's not like that, meaning A and C are already wrong based on that regard, okay? I'm left with B and D. But comparing B and D, get this. If it's falling from rest, it means that the initial, okay, whenever you consider this projection, it means that the initial UY will actually be equivalent to 0, but UY will be greater. Okay, so UY is greater here. Okay, is greater when hitting the ground. Okay, why is this? Acceleration means the velocity is actually increasing. So if it's going to have an acceleration downwards vertically, it means that if it's going to have a value of 0, because it's horizontal, we can't resolve it. So it means that if Uy is goes to 0, it's going to keep on increasing until it strikes the ground with a very high velocity. Okay, so the acceleration, which is equivalent to g, is actually going to cause its velocity to increase as it reaches the ground, meaning I need an initial gradient that will be 0. Let's go to our graphs, right? So if I analyze this, the initial gradient has to be 0. So if I were to draw a tangent, remember, the gradient of a displacement time graph is actually velocity. So if I were to draw a tangent over here at the beginning here, okay, something like that, that tangent is actually 0, meaning that V is actually equivalent to 0 at the start of my journey, which is quite true, but my velocity is starting at 0. But here, B is wrong, because if I draw my tangent, I'm already starting with an initial velocity, which is not 0, which makes B quite wrong, but it makes D correct because the initial velocity is 0. And the velocity is going to increase. As you can see, the gradient keeps on increasing. The gradient at this point is quite different from the gradient at that point. Okay, so the gradient at that point is quite different from the gradient at that point. The gradient keeps on increasing, and the velocity will keep on increasing. So get this, the initial velocity is 0, so the initial gradient has to be 0. Okay, the final velocity has to be higher than the initial, so the gradient needs to keep on increasing. That makes our answer D. Very important. I'll move on to question number 7. We've been given a device for spraying paint that consists of a box with its faces horizontal and vertical. Okay, one of its vertical faces contains small holes. So this face basically contains these different small holes. Okay, so these are the small holes, right? And paint is fed into the box under pressure. Very important, via a vertical tube, and it exits through the holes as fine streams moving vertically. So pressure, the paint is just going to exit these holes. Okay, so it's just going to exit these holes, right? But we're pouring the paint over here, but it's going to exit those holes moving horizontally. So as you can see here, this is basically horizontally, right? So this is horizontally. Okay, very important. The paint is ejected at a speed, so we're given the speed, and it's through 400 holes, each with the area of 0.4, and we've been given the density of the paint. So we've been asked to find the horizontal force required to hold the device stationary as it is ejected, as it ejects the paint. Very important. Okay, so if we analyze this question, what are we given? We're given the velocity, okay, we're given the area, and we're given the density, and we're given the number of holes that is coming out. Okay, so get this, if the horizontal force that's required to keep the device stationary as it ejects the paint, that force has to be equal to the force that the paint is going out. Okay, so the force of paint right, should be equal to the force that is horizontal. Okay, so as the paint tries to go out, this thing is going to exert another force backwards so that it remains stationary. Okay, so as the paint moves out, right, basically as the paint moves in that direction, it's going to exert a force backwards so that it can stop it. Okay, but we know that force is actually the rate of change of momentum. Okay, but this is momentum. Okay, so this is basically momentum. Okay, so force is the rate of change of momentum, right? Very important. All right, but the rate of momentum is actually m delta v, okay, divided by t, right? So you just need to know that force is the rate of change of momentum. But get this, guys, momentum does not only change based on change in speed alone, right? Basically, this equation can be written in two ways, right? Some of the way it's written is because it uses a certain method of differentiation that you haven't quite done. So I'll just give you the formula, but it's very important for you to just know it. It's m dv divided by dt plus v dm divided by dt. Okay, so this is a very important formula, but what it basically means is that, okay, for force, we say force is the rate of change of momentum, but momentum can really change in both ways, right? You can change the mass of something. Momentum will keep on changing because remember, momentum is a product of mass and velocity. If the mass changes, the momentum changes also. If the velocity changes, the momentum also changes. So a change in velocity and a change in mass can cause a change in momentum, right? So it's very important for you to be thinking of those ideas. But is our speed changing here? Get this. The speed is not changing because it's ejected at that same speed. But the mass of paint that goes out might change, right? But the velocity of the paint is not going to change. Meaning in this equation, all of this is basically going to be equivalent to 0, right? So basically our force is actually V dm divided by dt. So get this, the mass is changing but the velocity remains constant. I just need you to be able to get that. But you know that density is actually equivalent to mass divided by the volume. Okay, so the mass is actually equivalent to the density. If the mass is changing, right, it means that the volume also has to be changing because the density always remains constant. It's still water, right? But I've said this is dm, so the volume actually has to change, right? So the force would therefore be equivalent to V, right? Rho times delta V divided by delta T, right? But this is the volume, okay? Right. So the force would be equivalent to the velocity multiplied by the density multiplied by the volume is actually the area multiplied by, the area is also remaining constant, multiplied by delta L, okay? Divided by delta T. But this, okay, this is also velocity, right? This alone is also velocity. Therefore, F will be equivalent to V multiplied by the density multiplied by the area multiplied by the velocity. Therefore, F will be equivalent to rho a v squared, right? So this is a formula that we often use very often when we're solving momentum questions, okay? So I'm just going to go through this. Like, remember, like I've said, the force is the rate of change of momentum. Get this, right? But momentum changes because of mass or because of velocity. So I can have two equations, m dv over dt plus v dm over dt, right? The mass can change, the velocity can change, or both can change, right? But in this case, the velocity is constant. So the change in velocity is actually 0. But the mass is the one that is changing. How? Because the volume that comes out is actually changing. I know that density is equal to mass over volume. Therefore, mass is actually equivalent to the density times the change in volume, okay? So the change in volume is really the area multiplied by the change in length. So the change in length divided by dt, that's actually speed, because s over t, displacement over time, that's actually your velocity. So your force would be your density times your area times your velocity. So very important for you to know these formulas, especially when you're solving a lot of paper 1 questions, okay? So if you look at this, we can find the force, but this is only for one hole. So it seems to multiply by 400 for all of these holes, okay? So our force would therefore be equivalent to, okay? So it will be equivalent to 400 multiplied by what is our area? It's 0.4, okay? 0.4 millimeter squared. So it's times 10 to the power of negative 3 squared, okay, multiplied by our velocity, which is 2.5 squared, okay. So it's basically 2.5 squared multiplied by our density, which is 900. That will give us an answer of 0.9 newtons. Okay, so this was a bit complicated, but you just have to get the idea that I can derive this equation, right? Most people just know this equation and they can apply them, right? That force is also density times area times velocity squared. But I would like you to just know where these things are coming from, not just memorize these formulas by head, okay? Moving on to the next question, question 8. Each diagram illustrates a pair of forces of equal magnitude. Which diagram gives an example of a pair of forces described by Newton's third law of motion? What does Newton's third law of motion actually say? Well, Newton's third law of motion states that if body A exerts a force on body B will exert an equal but opposite force on body A. So with Newton's third law, you basically need to know these things, right? The first thing that you need to know is that these forces should be of same magnitude, okay? So these are what I call the characteristics of Newton's third law pairs, okay? So these are basically Newton's third law pairs. Let's write them down. Okay, so these are Newton third law pairs. Okay, so Newton's third law of pairs have the same magnitude, number one. Number two, they are opposite in directions. Okay, opposite in direction. Okay, number three, they are of the same type. Okay, if they're gravitational forces, they both have to be gravitational forces. Okay, number four, they act, okay, on different bodies. Okay, they act on different bodies. Okay, so basically these are the proper characteristics of Newton's third law pairs. So these questions have been coming a lot. So you basically need to know these four things. They have to be the same magnitude, opposite in direction, same type, act on different bodies. Okay, so let's start with A. You have a total resistive forces acting backwards, but a total driving force acting forward. Now I need you to have your checkbox and tick these things through. Are these forces the same magnitude? Okay, so we're just going to have a little acronym that we can use. Okay, so it's M, right? Your O, your S, right? And your A. Okay, so MOSA. So magnitude, opposite in direction, same type, act on different bodies. Okay, so we're going to check this out for all A, B, C, D and see which one satisfies all these conditions. So the first one for these, are these two forces of the same magnitude? That's correct, because the resistive forces might be equal to the driving force if it's moving at a constant velocity. So I'm just going to assume that it's going to be moving at a constant velocity, right? But they can be different provided that driving force is greater actually than the resistive forces. Okay, are these two forces opposite in direction? Of course. Are these forces the same type? They're not exactly the same type because this is a driving force, but this is a resistive force, right? So it's a bit tricky. Are they acting on different bodies? Oh, no, not exactly, because they're all acting on this car, right? This car is basically producing the driving force and the resistive force are also acting on that car. So this is not showing a pair of these forces, right? We go here, okay, we write our abbreviation, right? We go here, we write our abbreviation, we go here, we write our abbreviation. Okay, so very important. We'll start here, right? Are these forces the same magnitude? They might, if the lift force is equal to the weight, so that the aeroplane doesn't come crashing down. Okay, are they opposite in direction? Very important. They are opposite in direction. Are they of the same type? Well, the lift is actually might be because of these engines, the thrust on the aeroplane. So we can't really say they're the same type as the gravitational force of the weight. So not exactly. Are they acting on the same body? Of course, because it's all acting on this aeroplane right here. Okay, sorry, it's all acting. Okay, it's all acting on that aeroplane over there, right? But are these forces, right, acting on different bodies? They're not, like I've said. So this is out, right? We go here. Are they of the same magnitude? They might be, right? Support force might be equal to the weight so that it doesn't crash down into the floor, okay? Or it doesn't float because the support force is greater than the weight, okay? Are they opposite in direction? Yes, of course. Are they of the same type? They're not, because the support force is actually a contact force, but the weight is a gravitational force. So this law is not met, right? Are they acting on different bodies? They're not. It's still the same box, right? So they can't be acting on different bodies. It's just one body, right? So they're not, right? So this is not a Newton third pair. This is not, right? But let's go to B, right? Are they of the same magnitude? They might be, right? Because the gravitational force that the Earth exerts on the moon might be equal to the force that the moon exerts on the Earth, right? Are they opposite in direction? They are, because one is acting here and the other is acting that direction, right? Are they of the same type? Guess what? They're both gravitational forces, so they're of the same type. Are they acting on different bodies? One is acting on the Earth and the other is acting on the moon. So yes, this is a Newton third pair. So whenever you see this question, always ask yourself, what is my mosa? What is my magnitude? Are they opposite in direction? Are they of the same type? Are they acting on different bodies? If it doesn't fit those criterions, it is not a Newton third law pair. And you can move on to the next one, right? You can also find other different laws of why they're third pair, but those ones will actually get you the mark for this question, okay? Move on to question number 9. Two bows, okay? They have the identical shape and size, right? Identical shape and size. So let's draw them, right? So this is bow A, okay? And this is bow B. Okay, over there, this is bow B, right? So they're identical, the identical shape and size. Okay, so sorry. So they have to be identical. So let's take that, right? Okay, something like that. Okay, so they have to be identical, right? So they have the same mass, right? But so they have to be identical. Okay, so they have different masses though, right? So let's say this is mass M and let's say this is mass 2M, okay? And they're falling through the same liquid, okay? So both of these are falling through the same liquid, okay? So let's put that liquid. Both of these are falling through the same liquid, okay? So let's put that liquid over here, right? So this is our liquid. They're both flowing through that liquid itself, okay? The sum of the drag force and the upthrust acting on each bow is equal to its weight, okay? So basically, get this, the upthrust is going to act upwards, okay? The drag force is also going to act upwards because they're falling down, and the weight is going to also act downwards, right? This is for this bow A as well as for bow B, okay? So let's name this bow B, okay? So this is just the same for bow A as well as for bow B, right? But they are identical in shape, but they just have different masses, okay? Which statements about the two bows is correct, right? The heavier bow has a large acceleration. We can't even talk of acceleration. Why? Because there is no resultant force. There is this word equal. The upthrust, the forces acting up are equal to the forces acting down. So A and B are wrong because there is no acceleration or deceleration. We're left with C, right? C states that the heavier bow is falling at the same speed, and D says that the heavier bow is falling at a larger speed. Okay, what is happening here? Get this. Mass is actually proportional to the upthrust, right? What do I mean by this? The upthrust is basically a force that originates as an object moves down, right? In a liquid, the liquid is going to exert a force moving up, right? And that force is going to sort of like try to push that object upwards, right? So Archimedes devised Archimedes' principle that the weight of the fluid displaced is actually equivalent, right, to the weight of the object itself, right, or the volume of the object itself, meaning that a larger mass is going to displace a greater weight, right? Get this. If I'll give you an example. If you have an elephant, right, okay, and you have, let's say, maybe an impala, right? You have two kinds of animals and they're going to drop in water, right? Obviously, an elephant is going to splash the water more and the impala is going to splash the water less, right? What this basically means is that the elephant had a greater mass, so it caused a greater upthrust, so the weight of the fluid displaced was actually greater. So because of that, it meant that the upthrust on the elephant was actually going to be greater. It was going to splash a greater amount of water. For the impala, not so much, because it's going to displace or going to cause a lesser upthrust. So the volume or the weight of the fluid displaced is actually going to be less, right? But you just need to know this, that upthrust is related to the mass. The greater the mass, the greater the upthrust, right? So get that. So basically, if bow B has a greater mass, right? So if the mass of ball B is greater than the mass of ball A, basically the upthrust of ball B has to be greater than the upthrust of ball A, right? Basically, because it's going to be bigger, right? But if the mass of ball B is greater than the mass of ball A, basically the weight of ball B is going to be greater than the weight of ball A, right? It's basic principles, right? If the upthrust is going to be greater, the weight is actually also going to be greater, right? So as it's trying to move down, the upthrust is also going to increase, right? But the weight is going to be so much greater, right? But that's going to cause the drag force to also increase, right? So if upthrust is going to increase, for all of these forces, right, to remain the same, the drag force also has to increase. So the drag force acting upwards has to be increasing, right? So the drag force, right, the drag force that acts on B has to be greater than the drag force that is acting on A, right? So since the upthrust of body B is going to be greater, it's going to displace a larger volume of the water, but the weight is also going to be greater, okay, because it's 2m, twice the weight. So the weight is going to be acting down, right? So for the drag force and the upthrust acting to be equal to the weight, it means that initially the upthrust was actually not even equal to the weight, right? Because the drag force was also included. So if the upthrust goes up, right, in order for everything to remain equal, the drag force should also go up so that these two, basically remain the same. Because you're saying that, okay, if your upthrust plus your drag force is equivalent to your weight, right? In order for this whole equation to remain balanced, if you increase your weight, right, your upthrust, you increase it, but not that much, because basically upthrust plus drag force has to be equal to the weight, right? So if you increase this basically has to just increase, right? So that this whole equation will remain balanced, right? Because the upthrust is not as big as the weight, right? So because it's being helped by the drag force, right? So the weight is going to increase down, the upthrust is also going to increase, so the drag force should also increase so that those two counteract the weight acting down, right? But we know that if the drag force increases of that ball, right, so if it's going to experience a greater drag force, we know that the drag force, right, is related to the velocity, right? So since the drag force is related to the velocity, it's actually going to fall down at a very larger speed, right? So the heavier ball is going to fall down at a larger speed than the lighter ball. Why? Because the upthrust is greater, the drag force increases. If the drag force increases, the velocity is also going to increase. So it's very important for you to be thinking about that. As the weight increases, the velocity also increase. Okay, very important. Moving on to question number 10. When we're given a perfectly elastic collision between two objects x and m, the mass of x is m and the mass of y is 4m. Object x travels at speed v before the collision, and speed 3 v over 5 in the opposite direction after the collision, and object y is stationary before the collision. So basically, momentum before, okay, so momentum before collision, okay, should be equal to the momentum after collision. Okay, so that should be equal to the momentum that is after the collision, right? So the momentum before is actually your mass, okay, multiplied by your velocity v. Since this is stationary, it's not going to have any momentum because it's stationary, and this is going to move in the opposite direction. So it's your mass multiplied by negative 3v over 5, but it's going to be moving in the opposite direction, plus, okay, 4m multiplied by vy, okay, multiplied by vy. So it's going to go to the other side, so mv plus 3v over 5 multiplied by m, that's going to be equal to 4m vy, right? So we cancel out all the masses, we're left with 3v over 5 plus v is equivalent to 4vy, right? So that's going to give you about 8 over 5 v is equivalent to 4vy, right? So if we cancel that on both sides, it's going to be a 2, so we're left with 2 over 5v. It's actually equivalent to vy, right? But the question has asked me to find the kinetic energy of y after the collision, right? I know that the kinetic energy is actually 1/2 multiplied by m multiplied by velocity squared, right? So it's 1/2. The mass is actually 4m. The velocity squared is actually 2 over 5 v squared, right? So that's going to be basically 1/2 multiplied by by 4, right? For M multiplied by 4 divided by 25 multiplied by V, right? So basically that's going to be V squared. So basically that's going to be 1/2 multiplied by 4 divided by 25 multiplied by V squared, right? So that's going to be 4 times 4. That's going to be 16 over 50 mv squared, right? So 16 over 50 mv squared. The answer is C. Okay, move on to question number 11, which is not a requirement for two forces to act as a couple. So again, for two forces to act as a couple, they need to satisfy the following requirements, right? They need to act in opposite directions, which is correct. They need to be equal in magnitude, correct? They need to produce a zero resultant force. Might be true, because if one force is acting down, right, and the other force is acting up, the resultant force is basically zero, right? And the two forces must act through the same point, right? But they shouldn't act through the same point, because we won't have a moment if they're all acting at the same point, right? So the answer is B. B is wrong, because it's not a requirement for forces to act as a couple. Moving on to question number 12, we've been given a uniform meter rule that is pivoted at the 34 centimeter mark, right? As shown, the rule balances when a weight of mass 64 is hung from 4.0 centimeter mark. What is the mass of the meter rule? So the mass of meter rule is going to basically act at this point here, the 50 centimeter mark, right? So it's basically going to act here, which is the weight of the ruler itself, right? But we know that the anti-clockwise moments, right? The sum of the anti-clockwise moments will be equivalent to the sum of the clockwise moments, right? So what are the anti-clockwise moments? If this is my pivot P, right? Basically, all these forces acting here, that's basically my anti-clockwise moments, right? And all the forces acting here, that's basically my clockwise moments, right? So my anti-clockwise moment is going to be that one, right? But I need to convert it into a force, 64 divided by 1000 multiplied by 9.81, right? And I need the distance from the pivot, right? If it's 4 centimeters, right, and that's 34, the difference is 30. So that's 30 multiplied by 10 to the power of -2. That should be equal to the weight that I don't know, okay? So the weight multiplied by the distance, which is, since it's 50 and that's 34, the difference is 16. 16 times 10 to the power of -2. So basically, the weight should be equivalent to, if you do the calculation, that's going to be basically all of that is 0.188352 divided by, okay, sorry, divided by all of that divided by 16 times 10 to the power of -2. That's going to give you basically 0. Okay, that's going to give you about 1.1772 newtons as your weight, right? But basically we know that weight is equals to mass multiplied by the gravitational force. The question asks us to find the mass, okay? So the mass would basically be 1.1722 divided by 772 divided by 9.81. That basically gives you 0.12 kgs, which is about 120 grams, okay? So which is C. So just a matter of you applying the principle of moments. The anti-clockwise moments will be equal to the clockwise moments, okay? Very important. Moving to question number 13. We've been given a volume of 1.5 cubic decimeters of water. So this is the volume of water, and it's mixed with this volume of alcohol. The density of water is that, and the density of the alcohol is that, right? The volume of the resultant mixture is actually 2.0 m cubed. What is the density of the mixture? So basically, guys, I need you to understand this. This is the easiest way that you can solve this. There are other methods that you can solve density equations, right? Especially density of mixtures, right? But I'm just going to teach you a very easy method. The other one is quite complicated, I think. But if you understand it about proportions, it's very good, right? But basically, right? So let's do this. Density of mixtures, right? So if you have two mixtures, mixture A and mixture B, right? Or even C, and you want to find the density when you mix them all together, right? You basically need the mass of A, right? And you also need the mass of B, okay? You also need the volume of A, and you also need the volume of B, okay? So basically, these are the things that you're going to be needing, right? The volume of A, okay, the mass of A, the volume of B, the mass of B. But what are you going to do with this? Well, we know that density is actually the mass divided by the volume, right? So if you're going to mix things up, so the mass would be the total mass, okay? The total mass divided by the total volume, right? Okay, so the total mass would therefore be mass of A plus mass of B divided by volume of A plus volume of B, right? So basically that is what you're going to be doing in order for you to find the density of mixtures. So guys, I would really highly recommend that you have a notebook or somewhere where you're writing these concepts down. With paper one, it's very tricky because some of these things, they're not really quite stated in the syllabus, right? You learn them as you do paper ones, right? So, for example, this concept of density of mixtures, it's a concept that you just have to know. If you have two density mixtures, A and B, this is how you find the density. So I'd highly recommend that as you see these concepts, write them down somewhere so that you can be able to remember them and be able to apply them. Whenever you see a question that's asking for the density of mixtures, you already know that for this question, what do I need? I need the mass of A, the mass of B, volume of A, volume of B, and you can find your density, right? So if you're going to ask yourself here, let water be A in our question, okay? So let water be A, okay? And let what else? Oh, let water be B, okay? That can work too. Let alcohol be A, okay? Let alcohol be A, right? So let's go. We're going to start with the mass of water, okay? The mass of water, okay, is basically mass of water. We don't have the mass of water, okay? The mass of water is density times the volume, right? The mass of water is basically the density of water times its volume, right? The density of water, which is basically 1,000, right? Which is basically 1,000 multiplied by the volume of water, which is 1.5, right? So that gives us a mass of about 1,500 kgs, right? The next one is the mass of alcohol, right? So it's the mass of the alcohol, right? So the mass of the alcohol is the density of the alcohol times the volume of the alcohol, right? So the density of the alcohol is basically 800 and the volume is 0.50, right? So 800 multiplied by 0.40, right? That's going to give you 400 kg. So you're basically done, right? So remember, the density of the mixture will be the total mass, which is 1,500 plus 400 divided by the total volume, which is 2, that gives you 950, right? So basically the answer is going to be D. So I highly recommend that whenever you see a question about density of mixtures, what is the total mass, what is the total volume, divide the two, you have the density of your mixture. Very important. An object is falling at a constant speed through a viscous liquid, and Fu is the upthrust acting on that object, right? So basically, the upthrust is actually equal to the weight of the liquid displaced, right? Without, like I've been talking about Archimedes' principle, whenever you have an object that is immersed in water, the weight of the liquid that's going to displace is basically going to be equivalent to your upthrust, right? So basically the upthrust is actually equivalent to that, right? So the upthrust is basically equivalent to the weight of the liquid displaced, right? So your upthrust will be equivalent to the weight of liquid displaced, which is A. Move on to question 15. We've been given an airport that is a mechanical system for moving luggage, okay? So the system using a horizontal lever to a horizontal conveyor belt, a sloping conveyor belt, and a lift and a frictionless slide. A suitcase is moved around the airport using this system, okay? So we've been given resistive forces that are opposing the motion to be negligible, so we're not going to consider them, okay? For which movement is the net work done greatest? So the net work done has to be greatest for that movement, okay? Okay, so let's think about this, guys. What is the work done, basically, right? The work done can be in different ways, right? So work can be done to overcome, okay? So work can be done, number one, to overcome frictional forces, okay? But get this, the frictional forces are negligible because the resistive forces are negligible. So basically, don't have work done to overcome frictional forces, right? Number two, work can be done to increase the gravitational, okay, potential energy, right? So basically you can increase work. You can do work by increasing the gravitational potential energy. Number 3, you can do work, right? So this is an increase. Okay, you can do work by increasing the kinetic energy. Okay, so if you increase the kinetic energy, if you increase the gravitational potential energy, you have done work, right? Very important. So let's look at this. If a suitcase is going to move up a distance of 8 meters at a constant speed, right, up a conveyor belt, right, what is going to change? What is going to be our work done? Well, basically the work done is going to be increasing the height of that airbag, right? So if we're going to zoom in, it's basically increasing it across this distance over here, right? Across this distance x, right? So basically that is what is going to happen. That is the whole work that is going to do, right? But you know that from a triangle, the hypotenuse is the longest side, right? So if the hypotenuse is 8, basically means that when I'm considering the work done in increase in gravitational potential energy, which is basically equivalent to m multiplied by g multiplied by h, since h is basically equivalent to, since h is basically less than 8, it means that my GPE, right, my gravitational potential energy, let's just say it's going to be x, right? So basically this is my gravitational potential energy in moving up these 8 meters, right? So it's going to gain gravitational potential when it's once at this point. Okay, now it has gained potential, it has gained its height, it has gone to this point, right? And the gravitational potential increase is basically GPE, which is actually going to be x, right? Let's go over here, right? It's not going to move because it's going to move a distance of 16 meters, but at a constant speed. Meaning that over here, from this point to that point, no work is done in kinetic energy. No work is done in GPE, right? Gravitational potential energy. The work done might be, just heating, basically, with thermal energy, or just no work is done at all because we have no force actually being applied. The conveyor belt is just moving that bag over there. So we can't even talk of any force being done at that point, right? Comparing these points A, right, these 2 points, work is done, but work done is actually going to be raising that 10 meters. So we have GPE, which is actually mgh, which is going to be, since the height is going to be equivalent to 10, the gravitational potential energy, let's just say it's going to be y, right? But already, y is already greater than x, right? Because x is just less than 8, but y is actually a distance of 10, right? If you're going to move from that point up until that point, again, the hypotenuse is going to be way less than 12, right? So it can't be 10, right? That difference doesn't make sense because if you look at this, right, there's going to be a very, very big difference over there, right? So it basically means that the height h that this is going to fall will not be the same as that 10 meters, right? It doesn't make sense because this height is actually way less than that 10 meters, right? So the work done is basically to increase the velocity, right? So as it's moving from this point, let's just say point A to that point B, the speed is going to increase because we've been told that it's an increasing speed downwards. But that speed is going to increase because it's going to lose gravitational potential energy from point A to point B. But again, the gravitational potential energy is less than mgh, which is when h is equals to 10. Basically, it means that the kinetic energy is also going to be less, right? So the highest gravitational potential energy that we have is when it's moving the suitcase at a distance of 10 meters vertically up on the left. So the answer will be C. Very important. Moving on to question number 16. We'll be given a car that moves along a horizontal road with a constant velocity v against a resistive force F. We know that power is basically the force multiplied by velocity. Where does this come from? Power is basically the work done per unit time, but work done is the force multiplied by the distance divided by the time. This is basically the velocity, right? So power is the force multiplied by the velocity. Okay, we know that. And we want to find the input power to the engine, right? So how do you find this? We know that efficiency, the power output, divided by the power input is basically going to be equivalent to your efficiency, right? But your efficiency is 25%, which is just 0.25, right? So power output divided by power input is going to be equivalent to 0.25. So your power output is going to be 0.25 multiplied by your power input. So your power output divided by 0.25 will be equivalent to your power input. So your power output is basically multiplied by 4 is going to be your power input, right? Because 0.25 is 1 over 4. So it's 4 times PO, right? But your power output is actually your force multiplied by your velocity. That is what you're doing, right? So essentially, Okay, so it's 4 multiplied by F multiplied by V, is actually your power input, right? Which is C. So basically what you're doing is you're increasing, you're moving at a constant velocity against a resistive force. So the power that you're doing, the power output, is for you to overcome that resistive force. How do you find it? Is your force times your velocity V. So your input power will basically be, your power output multiplied by 4. Okay, moving to question number 17. We've been given an object of mass 0.40 that is projected along into the air and follows a curved path along the horizontal ground, right? The object takes a time of 1.5 to move along its path, okay? So the object lands a horizontal distance of 18 meters from its initial path. Air resistance is negligible. Okay, what is the kinetic energy of the ball at its maximum height? We know that at the maximum height, the only velocity that we have is in the horizontal, right? This is the only velocity that we have, right? So how do you find that velocity? We know that the range is equivalent to your velocity in the x multiplied by the time. Why? You've moved the distance of 18 meters in the x, okay? And it took you a time of 1.5. So basically, what velocity were you moving at? That is basically what we're asking here. So your value of Vx would basically be 18 divided by 1.5, which would just be 12 meters per second. So essentially, you're moving at 12 meters per second, right? So if you have that and you want to find the kinetic energy, we know that kinetic energy is 1/2 multiplied by the mass multiplied by the velocity squared, right? Which is half. The mass is 0.40, okay, multiplied by 0.40 multiplied by the velocity, which is 12, okay, 12 squared. That gives you a total of approximately, I think, 28.8, which is about 29 joules, right? So the answer is D. So get this, right? You have to find the speed whenever you have to talk of kinetic energy, and the speed we found it is 12, and you apply the law to find the kinetic energy at that point, right? Very important. Question 18, we're given a metal wire that is length of 5.2, diameter 1.00, and the Young modulus is 360 gigapascals, okay? So we've been given, what else have been given? We've been given the extension, and we've been asked to find the force applied. So basically, we know that the Young modulus is the ratio of stress, okay, stress to strain, right? That is basically what the Young modulus is, but, okay, but stress is actually equivalent to the force divided by the area, okay, and, okay, and strain is basically equivalent to the extension, okay, divided by the original length, okay. So basically, our Young modulus would be equivalent to our force divided by our area, our extension divided by our length. That would be our force multiplied by our length over our area multiplied by our extension. That's going to be our Young modulus, right? So basically, our Young modulus would be equivalent to force multiplied by length, area multiplied by the extension. So the Young modulus basically, if you look at this, the Young modulus is going to be 360 gigapascals. So it's going to be 360, but giga is basically times 10 to the power of 9. As you can see on the prefixes that I put on the screen, giga is times 10 to the power of 9. And that's going to be equivalent to your force. What is your length? 5.2. What is your area? Okay, so area is, do we have our area? We're given our diameter, which is 1.0. Okay, so our area is basically pi, right, of our diameter, which is 1.0, okay, 1.0 times 10 to the power of -3 divided by 2 squared, okay, multiplied by our extension, right, our extension, which is basically what's our extension? 7.2, right? So 7.2 times 10 to the power of -3, right? So basically it's going to be 360 times 10 to the power of 9, your force, okay, times 5.2 divided by 5.6548 times 10 to the power of -9, right? So your force F is going to be 360 times 10 to the power of 9 times 5.6548 times 10 to the power of -9 divided by 5.2. So your force F is going to be therefore equal to 391, about 490 newtons. That's about 3.9 times 10 to the power of 2 newtons, right? So the answer is going to be B. So just think about this, right? What is your Young modulus? Is stress over strain, and Stress is force per area. Strain is the extension per inch original length. What is your Young modulus? You then express that and you can be able to find the value of your force. Okay, very important. Question 19. We've been given that graph and we've been asked to show that, we've been asked to find the work done in stretching the spring to reach that point L. So basically, the work done is the area underneath the graph, right? So basically, the area underneath that graph, okay? So basically, the area underneath that graph represents the work done, right? So how do you find the area of that graph? It's actually a triangle, right? And the area of a triangle is actually half base multiplied by the height, right? So it's half, your height is F, your base is L1 minus L0, right? So the answer is B. Moving to question number 20. We've been given a progressive wave. Let's move on. We're almost halfway through. We've been given a frequency of 1.5 kilohertz that's traveling in a medium at a speed of 340. What is the minimum distance between 2 points on a wave that is a phase difference of 70 degrees? Basically, we know that the phase difference, when we want to calculate it, is 360 x over lambda, right? So the phase difference, if you have 2 points, right, is basically the distance between those 2 points divided by the wavelength multiplied by 360 degrees. You get your phase difference. But we've been already given that the phase difference is 70 times 360 over x multiplied by lambda. So 70 multiplied by lambda divided by 360 should be our value of x, right? But how do you find the value of lambda? We know that v is actually f over lambda. So lambda will actually be v over f, right? So your value of v is 340. Your value of your f is 1,500, 1.5 kilopascals, basically 1,500, right? So that's going to give you a value of lambda of approximately 0.226 meters, right? That is your value of lambda. So how do you find your value of x? It will basically be 70 multiplied by 0.226 divided by 360. Basically going to give you a value of x of approximately 0.04407 meters, about, I guess, 4.4 centimeters, right? So it's 4.4 centimeters. The answer is A. So just be thinking of those laws, right? Phase difference is actually 360 x over lambda. It can also be 360 t over lambda, right? Like that. Your phase difference can also be 360 t divided by time. But this is only for a displacement time graph, right? So if it's a displacement time graph, that's when you use that. But your phase difference is actually 360 x divided by lambda, and this is when you're doing a distance, displacement time graph, right? So very important for you to be thinking of that. Graph 1 shows the variation with time of the displacement at a fixed distance along a progressive wave. Graph 2 represents that same wave and shows the variation with distance of a displacement at an instant in time. Okay, what is the speed of the wave? Again, we've been given another one. We know that v is equivalent to f lambda, right? But f is actually 1 over t. So lambda divided by t is actually going to be your speed. What is your lambda? Lambda is actually the distance from this point to that point, right? Two adjacent points in phase, or it's just, from one crest, you make another crest, you make a trough, you have arrived at one lambda, which is basically 120 divided by time. Again, it's the same, 0.40. That gives you a speed of 300 centimeters per second, right? So the answer is D. A vehicle moves with constant velocity along a road towards a direct observer. The observed frequency changes as the vehicle moves past the observer. Which phenomenon experiences the change in frequency? It's not diffraction. What is diffraction? Diffraction is the spreading of a wave when it passes through a slit. So it spreads into the geometrical shadow, as you can see over there, right? The wave that I have is actually, right? So as you can see over there, the wave is actually spreading into its geometrical shadow, okay? Interference is basically you have a wave, you have another wave, they meet at a point, and the resulting displacement is actually the sum of those individual displacements themselves. That is basically what interference is. Polarization, I've done a video on Malus' law. I would highly recommend that you watch my video. I really explained well the concept of polarization. I also solved some questions regarding polarization, and you can watch my videos in my channel, as you can see on the screen, regarding how we can be able to answer questions of polarization. But basically, polarization is the restriction of a wave vibrations to one direction only, right? And the Doppler effect is basically the apparent change in the observed frequency due to relative motion between the source and the observer, right? So basically, our answer becomes D. Okay, move on to question 23. When we're given a wave that has a wavelength of 2.1 centimeters, that's basically 0.02 meters. And as you can see over there, the one that fits is the microwave. Again, with electromagnetic spectrums, it's very, very difficult. Find a way of memorizing these in a way that makes sense to you, right? Like I've given you on the screen, these work in almost all cases, but really, you have your test book. You can go certain, platforms online and be able to actually get, these things in a way that makes sense to you. Again, this is only part of physics where there can't be any way to break it down, right? You just have to memorize those ranges by your head, right? But it takes time. You'll be able to get it through, right? So the answer is B, microwaves, right? Okay, another question on polarization, basically Malus' law, right? So the filters are positioned so that the source appears at its brightest, right? So the source is appearing at its brightest. One of the filters is then rotated clockwise, and the other filters is rotated anti-clockwise, okay? Through the same angle, right? How does the source appear when the filter have been rotated 90 degrees and 180 degrees from their initial position? So basically, this is their initial position. So I want you to look at this, right? So this side is basically a bit, longer than that side, right? So what I'm getting from this is that I can basically assume that, this polarizer is horizontal, right? That's basically what I'm going to assume, right? That this polarizer is basically horizontal. If it was going to be vertical, it was supposed to be positioned vertically, right? So if it's positioned horizontally, which it is, right? It means that it's basically something like that, right? So basically something like that, right? And this is going to form 90 degrees, right? And it's appearing brightest. What does this tell me about my light? It tells me that my light is actually, if you get that, is actually horizontally polarized. So my light is coming like that, horizontally polarized, right? But the first thing is I'm going to rotate my filter 90 degrees from the initial position, right? One of them, okay, so one of them I'm going to rotate them clockwise. The other one I'm going to rotate anti-clockwise. So if I'm going to rotate this anti-clockwise, it's going to be like that. If I'm going to rotate this clockwise 90 degrees, it's also going to be like that, right? But my light is coming in horizontally. If it tries to enter there, the polarizer says you can't pass through, no light goes through. So the I naught over here, okay, so just the I that we detect over here, so it's going to be equivalent to 0, right? So it's going to be darkest and darkest. So the answer is C and D, right? But if we're going to rotate it 180 degrees, so basically it's like that, right? So if we rotate it like that, that's 90 degrees. If you rotate it like that, that's another 90 degrees, right? So it's just going to come back to its original position like that. That is also going to come back to its original position if you rotate it clockwise like that. If you rotate that anti-clockwise, right? So they're just going to come back to the initial positions. So it's also going to be brightest. So the answer is going to be C, right? So it's going to be darkest when it's 90, brightest when it's 180. Move on to question 25. We've been given the diagram shows a string stretched between fixed point A, fixed point X, and fixed point Y. The diagram shows a string stretched between fixed point X and fixed point Y, and there's a stationary wave formed on the string, okay? The solid curve shows the spring at a position of maximum at time t is equal to 0, okay? So this is actually when time t is equal to 0. The dashed line shows the other positions of maximum displacement, okay? The straight center line shows the mean position of the string. Point S is directly above point P. So point S here, directly above point P, okay? Point T is directly below point Q. Which statement is true? Okay, let's see. A short time after T naught, point R will be displaced. Point R will be displaced. Well, that's a node, okay? A node is an area of minimum displacement. So a node can't be displaced because it's just going to, stay fixed. Let's go to C. The distance between P and Q is one wavelength, okay? P and Q. This is basically an antinode. That is basically an antinode. The distance between antinode and antinode is not a wavelength, but it's rather half of a wavelength, right? So basically, C is about wrong, right? D, the 2 points on the string that are equal distances from R vibrate in phase, right? So equal distance from R, It's basically somewhere here and somewhere here. Let's say it's point A and point B. But we know that, if for a stationary wave, an antinode and the nearest antinode, okay, so, but basically, we know that for a stationary wave, right, if you're going to have an antinode, right, something like that, right, an antinode, an antinode, an antinode, basically, adjacent antinodes are actually vibrating out of phase with 180 degrees, right? Another antinode and another antinode have a phase difference of 360. They vibrate in phase. So if an antinode is moving down, the next antinode will be moving up. The next one will also be moving down. So the one moving down and the one moving down are in phase. They're all moving down. But the one moving up and the one moving down are in antiphase with a phase difference of 180. Okay, so they can't be vibrating in phase, right? So a short time t, point S and T will move in opposite direction. This is true because point S will be moving up, right? Might moving down, but point T will also be moving up. So in a stationary wave, as one loop moves down, the other loop will move up, right? So the answer is B. We've been given the variation of intensity along a stationary wave as shown. The speed we've been asked to find the frequency. So we know that V is actually equivalent to F lambda. Okay, so we've been given 340 divided by lambda should be equivalent to the value of F essentially. Basically, so let's look at this. This is a node, right? There's an antinode, area of maximum intensity. This is basically, all of that is an antinode. This is basically going to be a node, right? And I know that from node to node, okay, that's basically half lambda. Okay, from an antinode to a node, that's basically 1/4 lambda. Okay, from an antinode to an antinode, that's basically half lambda. Okay, from a node, an antinode to another node, okay, that's basically and another node, okay, that's basically going to be lambda. Okay, all of that is basically going to be lambda, right? So in node to a node, that is going to be half lambda. So from here to here, that's going to be half lambda. That's going to actually be equivalent to 10 centimeters, right? So lambda is going to actually be 20 centimeters, in fact, if we're going to look at it from that angle, right? So the value of F, very important, is going to be 340 divided by 20 times 10 to the power of -2, I think. Okay, so that's going to give my value of F of approximately 1,700 hertz. 1,700 hertz, that's A. Question 27. An experiment is set up to demonstrate the diffraction of wave. Okay, we're almost done with waves, right? An experiment is set up to demonstrate the diffraction of water waves in a Ripple tank. The wave passed through a gap of width W, and some diffraction is observed. Okay, the wavelength is now doubled. What is the new gap width needed to cause the same amount of diffraction as before? So this is part of your syllabus. They expect you to know the effect of gap width on the amount of diffraction that will be occurring. So get this, guys. Whenever, okay, so if, as you can see over there, that's diffraction occurring. So whenever the, so get this, whenever the gap, let's say this is X, right? And you have a light, right? Or a water wave, basically Ripple tank is much easier, that has a lambda, basically this lambda, right? If the lambda, okay, is approximately equal to the X, right, the gap, that is when you have the highest amount of diffraction. Okay, when, get this, when the slit, the value of X, the gap width, is approximately equal to the lambda, you have the greatest amount of diffraction. When that is not true, you have the least amount of diffraction. When does this happen? Whenever the gap is bigger. Okay, so if the gap is bigger than the wavelength, right? So if the wavelength is like that, like that, like that, like that, if the gap is way bigger, we're going to have, so if basically if X is greater than lambda, we're going to have diffraction to a lesser extent. Okay, but if the gap is way small and the wavelength is very big, right? If this is way bigger than this, no wave will pass through. It's so small, and no wave is actually going to pass through through that, right? So very important for you to understand that. So if we're going to double our wavelength, we should also double our width, because, well, actually the width has to almost remain proportional, right? Approximately equal, to the lambda. So if I double the lambda, I must also double the wavelength, right? Sorry, I must also double the gap width. If I double the lambda, I must also double the gap width. So the answer is C. Very important for you to understand that. I'll move on to question 28. Two current electromagnetic waves are traveling in a vacuum. They meet at a point. At this point, they have different intensities, right? Basically, we know that intensities are proportional to Ka squared, right? So if intensity is different, right? So if this intensity is different, it basically means that the amplitudes, okay, basically means that the amplitudes are also different, right? So they cannot have the same amplitude, meaning that the answer is B. They cannot have the same amplitude. But why is A, C, and D wrong? Well, if waves meet at a point, they're going to have a constant phase difference, that's for sure. Because they're going to meet in phase and they're going to superimpose, right? If waves was coherent means that they actually have a constant phase difference, right? If waves are coming from one source, right, they're basically going to have the same frequency, because if we're going to produce coherent waves, they need to have the same frequency. If waves are going to meet at a point, they need to have the same speed, right? What do I mean by this? Well, imagine a lorry and a truck, right? If a lorry is very fast, it's never going to meet a car that's moving very slowly. So two waves, for them to meet, they need to have the same speed, right? So very, very important for you to be thinking of that. Moving to question 29, we're almost done. Question 30. Okay, so question 29, we're given a parallel beam of light that is this wavelength, right? That is incident normally on a diffraction grating. The distance between the adjacent slits is actually 2.0. So this is the value of D. A screen is placed parallel to the grating, a distance of 1.50 from the grating. Third order diffraction maxima are observed at the two ends of the screen. What is the distance between the two ends of the screen? So what do they want us to find? They want us to find this particular distance over here. How do I find this? If I have 1.50, I can use trigonometry. Get this. If this is the angle theta, right? This is the opposite. This is the adjacent, right? So basically, I know that tan theta is actually equivalent to my opposite divided by my adjacent, right? So my opposite will basically be my adjacent multiplied by tan theta. My adjacent is 1.5 multiplied by tan theta, right? So I will use all that information to find the value of theta. Basically, the golden rule for diffraction grating, whenever you see the word grating, one equation must come to mind, and one equation only. D sine theta is equivalent to n lambda, right? So that's the equation that should be coming to mind. We know that D sine theta is equivalent to n lambda. So theta is basically the arcsine of n lambda divided by the value of D, right? So theta will basically be the arcsine, okay, the arcsine of the value of n, which is 3, the value of lambda, which is 600, times 10 to the power of negative 9. The value of D is approximately, I think, 2.0 times 10 to the power of negative 6. 2.0 times 10 to the power of negative 6. So the value of theta, therefore, has to be 64.20 approximately degrees, right? So once you have the value of theta, we then go to say the opposite would therefore be 1.5 multiplied by tan, okay, 1.5 multiplied by tan of 64.2. That's basically going to be 1.5 multiplied by about, tan 64.2. That's going to give you about 3.1, right? So it means from here to here, okay, from here to here, it's actually 3.1, right? So from here to here, it's also going to be 3.1. So the total would therefore be 3.1 multiplied by 2, which is going to be 6.2, which is a D. So the first thing we had to do was use trigonometry. We know that theta, what we want to find is the opposite over the adjacent. So how do you find the value of theta? We use the diffraction grating. D sine theta is actually n lambda. Once you have the value of theta, we applied trigonometry. Tan theta is the opposite over the adjacent. And then we found the value of theta, essentially. Very important. Question 30. A metal wire is connected between the terminals of a battery and there is a current in the wire. Which statement is correct? Basically, electrons move from the negative terminal to the positive terminal. You need to get this, right? So electrons move from the positive terminal to the negative terminal. So A is correct, right? But B, since that negatively charged nuclei move from the negative terminal to the positive terminal. A nuclei, how is a nuclei negatively charged? It doesn't make sense because electrons orbit, the shells, right? So it doesn't make sense to tell me that, the nuclei is negatively charged. So B is basically wrong. C, the positively charged electrons move from positive to negative. Positively charged electrons, that doesn't make sense, right? Positrons, that's not going to work, right? So it can't be positively charged electrons, right? Positively charged nuclei, it still doesn't make sense. Why is it moving? It doesn't make sense. Electrons are the ones which carry charge, and they're the ones which actually move, but they move from a negative terminal to a positive terminal, right? Very important. Question 31. We're given two resistors of resistor R and resistor 2R. But this is the total resistance, right? The total resistance that we're saying 12 squared divided by 36. So what do we need to do? We basically need to know, we know that since they're in series, right? The total resistance, okay, so R total will basically be R times 2R divided by R plus 2R, right? So that's going to be 2 over 3R. Okay, so that's our total resistance. So 2 over 3R will basically be equivalent to 12 squared divided by 36. So R will be equivalent to 12 squared divided by 36 times 3 divided by 2. Okay, so the value of R will basically be equivalent to 144 divided by 36 times 3 divided by 2. Okay, that's going to give you an answer of approximately 6.0 ohms, right? So that's going to be 12 times 2, 24. 24 into 144 is going to be 6, right? So the answer is going to be D. Okay, moving on, we've been given a wire of length 3 meters. Resistivity is that. Potential difference we're given so that it has a current of 1.4. What is the cross-sectional area of the wire? We know that resistance is equivalent to rho L divided by A, right? So this is our first equation, right, that we're going to be applying, okay? We also know that V is equivalent to IR, right? So this is our second equation that we're going to basically be applying, right? So the value of R will basically be 12 divided by 1.4, okay? That's going to be about 8.57 ohms, right? So once you have the value of R, we just want to find the value of A. The value of A will essentially be the resistivity multiplied by the length divided by the resistance, right? The resistivity is 4.9 times 10 to the power of negative 7 times the length of 3.0 divided by 8.57, right? That's going to give you 1.7 times 10 to the power of negative 7. The answer is B, right? So basically, two formulas. Resistance is rho L over A, V is equal to IR. Use those two formulas and you find the value of your cross-sectional area. Very important. Moving to question 33. A cell of negligible internal resistance is connected in series with a thermistor, a fixed resistor, and an ammeter. Okay, so what do we have here? We have a cell, basically like that. So we have a thermistor, something like that. Okay, so we have a thermistor, okay, like that. Okay, so this is our thermistor, and we have a fixed resistor. Okay, so that's a fixed resistor. Okay. Then we have an ammeter. Okay, so we should have an ammeter over here. Okay, and we have, yeah, that's basically it. We go back to a circuit, right? And the thermistor is placed in a beaker of water, right? So let's go to a thermistor, and we're going to place it in a beaker of water, right? So like that. And we're going to place it in a beaker with water. Okay, so basically something like that, right? So this is our water over here, right? And the temperature of the water is slowly increased. So we're going to heat it up, right? So we're going to heat over here and increase the temperature of the water. And the graph of current against temperature is plotted, right? Which graph shows the variation of I with T. So basically, for a thermistor, you need to know the following things, right? If you have a graph for a thermistor, okay, the resistance and the temperature graph, how is it going to look like? It's going to look basically like that. As the temperature increases of a thermistor, the resistance actually decreases. But you know that V is actually equivalent to IR. Therefore, the current is directly proportional to the inverse, right? Direct proportional to 1 over R. So, or current is inversely proportional to to the resistance, right? If you decrease the resistance, you have to increase the current. So as temperature increases, if the resistance is actually decreasing, right, it basically means that your current needs to be increasing, right? So as the resistance decreases, your current has to be increasing, right? So where is current increasing? It's only in B, right? This is decreasing, right? This is decreasing, that is decreasing, right? So the only answer is going to be B. Very important. 34. When we're given a battery with internal resistance that is connected to a parallel arrangement of two resistors and a switch as shown, what happens to the voltmeter and the ammeter reading? Okay. So basically, whenever you close the switch, so let's close it like that, right? These two are going to be in parallel, right? So these two are basically in a parallel connection. Okay. So what's going to happen? Whenever you connect things in parallel, the resistance is actually going to be smaller than the biggest resistor. What do I mean by this? Well, since you're going to, you say 1 over R, 1 over R, 1 over R, the total resistance is going to be way, way smaller than the biggest resistor that you've got, right? So whenever you connect things in parallel, basically you just need to know this. The resistance is actually going to decrease, right? So the voltmeter reading, what's going to happen is that, well, we know that V is actually equivalent to IR, okay? So as the resistance is going to decrease, as this is going to decrease, like I've said, this is actually going to increase because they're inversely proportional, because this is remaining constant, right? Okay? So basically, those are the relationships that will be going on, right? As the resistance decreases, the current increases so that V remains constant, right? So its current is going to increase, the ammeter reading is going to increase, and it's going to increase, right? So B and D are wrong, okay? But get this, okay? Since the ammeter reading is going to increase, right? Sorry. B and D are the ones which are wrong, right? Because B and D are saying that, you know, the ammeter reading is decreasing, but the ammeter is actually going to increase, right? So what's going to happen to the voltmeter reading? Well, this is basically going to give me what I call my V terminal, right? So this is my V terminal. What voltage am I going to use in the whole circuit? That's what I'm going to get here. But this loss volts over here is actually going to increase, right? Because as current increases, right, the V loss is actually going to increase. You have to agree that the V loss is going to increase because the current is actually increased, right? So if V loss is going to increase, the V terminal is basically is going to decrease, right? So the voltmeter decreases, the ammeter reading increases, the answer is A. So get this. As the resistance decreases, whenever you connect a parallel connection, the resistance is smaller than the biggest resistor. So the resistance in series is way bigger than the resistance in parallel. If the resistance is going to decrease, the current is going to increase. If the current increases, what it means is that the V terminal is going to decrease because the loss volts is also going to increase. Where do the loss volts come from? They come from the internal resistance within a battery, because the battery contains chemicals, and the chemicals are going to have internal resistance. So that's the one that causes the V loss. Okay, so very important. Question 35. Basically about Kirchhoff's first law. Okay, the sum of current entering a junction is equal to the sum of current leaving it. Basically, we'll be conserving charge, right? So Kirchhoff's law, conservation of charge. Kirchhoff's second law is basically conservation of energy, right? Moving to question 36. When we're given two resistors, okay, moving to question 36. We've been given two resistors that have a combined resistance of 34 when they're connected in series. So let's connect these things in series. So resistor X, okay, and resistor Y. And the combination, whenever things are in series, we add them up. So X plus Y is actually going to be equivalent to 34. But then, when they're now connected in parallel, okay, so connected in parallel, it's basically going to be like that. This is X, right? And this is Y, okay? When they're now connected like this, the total is basically, remember, product over sum, 1 over R, 1 over R. Basically, whenever we have two things, it's product over sum. XY over X plus Y is actually going to be equivalent to 7.4. Okay, so this is your first equation. and this is your second equation. So how do you solve them simultaneously? Well, basically, get this. Xy is going to be 7.4 multiplied by x plus y. Okay, xy is basically going to be 7.4 multiplied by 34. So xy is going to be 7.74 multiplied by 7.4. That's basically going to be 251.6, right? So this is going to be equation 3, right? So I haven't done anything. If things are in series, I add the resistances. X plus y is 34. If things are in series, product over sum, xy over x plus y is 7.4. Cross multiply both sides by x plus y. So 7.4 times 34 is actually 251.6. So xy is 251.6. Okay, so get that. So y is actually going to be equivalent to 51.6 divided by x, right? So this is going to be the value of y, right? But I can substitute this value of y over here, right? So if I substitute that, I know that x plus 251.6 divided by x is now going to be equivalent to 34. Multiply the whole equation by x squared is equivalent to negative 251.6x plus 34. Both of them go that side, 34x, right? So, okay. So if I'm going to multiply both sides by x, I have x squared plus 251.6 is going to be equivalent to 34x, right? That goes that side. X squared minus 34x plus 251.6 will be equivalent to 0. So how do I find the value of x? It's negative b plus or minus the square root of b squared minus 4ac divided by 2a. So this is getting like a little mathematical, but remember, it's just, applying the quadratic formula. So here we have negative 34 plus the square root of negative 34 squared plus, minus 4 times a, which is 1 times 251.6 divided by 2 times 1. That's going to give me a value of x of about 23 ohms, right? So if the other one is 23, the other one has to be 11, right? So y has to be 11, right? Because x plus y has to be equal to 34, right? So it has to be 23, right? So a bit complicated, but we just had to manipulate our variables, get a quadratic equation, and be able to solve it out, right? Very important. Question 37. We've been given a potentiometer circuit that is used to investigate the EMF of a cell X. The EMF is known approximately to be 0.50. How do you find the expression for the approximate length of QP? So how does a potentiometer work? Well, basically, for potentiometer, for this galvanometer to read 0, the EMF of this cell should be equal to the voltage that would be over here. So VQP should be equivalent to the EMF of that. But if this cell is an EMF of 0.50, it means that VQP, so VQP, okay, will be equivalent to also 0.50, right? But it also means that QP divided by QR multiplied by 2.0 should be equivalent to 0.50, right? So it means that QP will be equivalent to 0.50 divided by 2.0 multiplied by QR. And this will be equivalent to QR divided by 4. And the answer is A. So basically, get this. For a potentiometer circuit, how they work is if the galvanometer reads 0, as the question has said that the galvanometer deflection is 0, it basically means that no current flows through in the downward circuit. The EMF of that bottom cell is equal to the voltage lost across that portion of your wire. If those two are equal, no EMF will be lost in the circuit, right? So very important for you to be thinking of that. Moving to question 38. Okay, so we've been given 4 nuclei, P, Q, and R and S, and which 2 nuclei are isotopes of the same element, right? So we can create a whole new table over here, right? So we can create of that, right? This is the number of protons, right? So 10 minus 5 is 5, 10 minus 6 is 4, 40 minus 6 is 8, 60 minus 8 is 8, right? So what is an isotope? Well, isotopes basically have the same, okay, number one, they have the same number of protons, okay, but what's different? The number of neutrons is the one that's different, right? So basically, look at this guys, right? R and S, right? Same number of protons, sure. 8 and 8, different number of neutrons, 8 and 8, 6 and 8, right? So basically, R and S have to be isotopes, ideally, because they have the same number of protons, 8 and 8, different number of neutrons, 6 and 8, right? So it's R and S. Question 38. We remember about beta negative decay is correct, right? So beta negative decay is basically a neutron changes into a proton and an electron and anti-neutrino are emitted. So basically the answer is A, right? A neutron changes into a proton and an electron and a neutrino is emitted. A neutron is only emitted in beta plus decay, right? A proton changes to a neutron in the nucleus and an electron and anti-neutrino are emitted. A proton does not change into a neutron, that only changes in beta plus decay. So that's wrong. A proton changes to a neutron and an electron and anti-neutrino are emitted. Again, a proton changing into a neutron is basically, again, beta plus, right? The easiest way that I know this is I know that, beta negative, okay, beta negative and beta positive, okay, negative, okay, positive, beta negative and beta positive. A way that I figured this out is that, since this has an N, right, that N basically states that a neutron, right, turns into a proton. So since beta negative starts with an N, that N means a neutron turns into a proton, right? Beta plus, as you've guessed it, starts with a P, P meaning what? That proton turns into a neutron, right? So now, without even thinking, whenever you hear the word beta minus, the word negative, ne, means that it's a neutron turning into a proton. Beta positive is a proton turning into a neutron, right? And you'll be able to, save space in your mind and be able to memorize other different things, right? Knowing that you can be able to remember that. What is the quark composition of a hydrogen nucleus? So get this, we have one proton and three nucleons, right? So basically we have one proton and we have two neutrons. But a proton is basically made of an up quark, and a down quark, right? And a neutron is basically made up of a down quark, and an up quark, right? So if we have two neutrons, it means that we have two down, down, up, okay? Plus we have an up, up, down, right? So basically I have 4 ups, right? But I have 5 downs, right? So it's 4 downs plus 1 down over here. That gives me a total of 5 downs and 4 ups, right? So it's 4 ups, 5 downs. The answer is A. Very important, right? So this was we're done. We've been working all these questions, and the answer is A. Okay, so that's it. Thank you guys for watching. I hope you do like my content, and please subscribe and comment, share and like, and I'll see you in the next one. So we're done with our paper. This is the last one. Thank you guys for watching my video. I hope you really enjoyed it. If there's anything that you found unclear, please put it in the comment section below so that I can be able to improve. Thank you guys. I'll see you in the next one.